Good morning or afternoon. Today we're going to talk about U-substitution, specifically with integration of indefinite integrals. And this is a technique that you will need to learn how to use. We already know some basics of integration, like we know how to use the power rule in reverse to add 1 to the exponent and divide by the new exponent. We know how to integrate e to the x. We know how to integrate 1 over x, that's natural log absolute x. We know how to integrate trigonometric functions, both sine and cosine. But what happens when things are a little more difficult and you need a technique to get you by? So we'll look at some problems with specific commonality here. All of them will utilize U-sub, and we'll do 3 examples together. But this is the key component that you need to write down. With every U-sub problem, this is the absolute key to recognize. The U-sub basic idea is you've got to set U equal to an inside function whose derivative appears. So you know what an inside function is, like a function in parentheses that's raised to the 3rd power, for example. That is an inside function. Or maybe you've got anything in parentheses that's raised to a specific exponent, or even like sine instead of sine of the x, like sine of 2x. That 2x would be an inside function. So again, step 1, whenever you're doing a U-sub problem, is to set U equal to an inside function whose derivative appears. That means once you set U, you have to contemplate its derivative. And as you look at the rest of the problem, when that derivative appears, you can piece this problem together. You can write the integral in terms of U. Now the reason that word appears is in quotation marks will become clear and apparent to you as we move up with regard to difficulty here. So we'll start easy, go to intermediate, and then go to a slightly more difficult intermediate, but not going to get too complicated on this particular video. So let's start with an example of an integral problem which requires U-substitution. This integral problem is the integral of sine squared theta cosine theta d theta. So the first thing you need to do is identify an inside function, something that is raised to a specific power. I see the inside function. The inside function is sine theta because it is the expression that is squared. So I want to set U equal to that inside function, sine of theta. The next step with the U-sub problem is to take the derivative of U. So the derivative of U with respect to theta looks like this. du d theta equals cosine theta. The next thing you want to do is multiply both sides by d theta, so you isolate the du and can write the du this way. du equals cosine theta d theta. Okay, so this is kind of like a substitution, like back in the old days when you did a substitution when you were solving systems of equations. You know that U equals sine theta, so when you rewrite the original, wherever you see a sine theta, you are going to replace it with the letter U. And where you see a cosine theta d theta, you are going to replace that part of the expression with a du. So the next step with U-sub problems is to rewrite the problem now in terms of U. When I do that, I'll get the integral of U squared du. Notice some things here. Namely, all of the circled items can be replaced in terms of U. In other words, I see sine theta in the original problem. Well, sine theta is equal to U. So in my rewrite, instead of sine theta, I have a U. In the original, I see a cosine theta d theta. That happens to be equal to du. So When I see the cosine theta d theta, I replace that with a du. The real advantage here is I didn't know how to integrate squat when I first got this problem. Now that I have rewritten the problem in terms of u, this is a pretty easy standard integration challenge. All I'm going to do is add 1 to the exponent and divide by the new exponent. You guys have been down this road before. U cubed over 3 plus c. Now that's not the final answer. I've got a back sub for u so that I can write this final answer in terms of theta. So I've got a back sub. Wherever you see a u now, I put in sine theta. My final answer looks like this. Sine cubed theta over 3 plus c. So again, I think it important to reiterate, how do you start a U-sub problem? Find an inside function whose derivative appears. That's the nuts and bolts of taking on a U-sub problem and completing it successfully. Let's look at a second example. This problem, we are going to integrate 1 plus natural log x quantity squared all over x. Well, it's pretty easy for me to locate the inside function here. At least I am hoping that the inside function that's going to work is 1 plus natural log x. Go ahead at this time and think of the derivative of 1 plus natural log x. Well, the derivative of that inside function is 1 over x. So I ask myself, does 1 over x appear? Some of you are saying, no, only x appears. Yeah, but it appears downstairs. So that is actually a 1 over x in disguise. We'll emphasize this in a moment. So let u equal the inside function 1 plus natural log x. That makes du equal to 1 over x dx. Notice the x is on the bottom. Notice the understood 1 is on top. So the fraction 1 over x does indeed appear in the original integrand. So I'm in great shape here. I'm now going to rewrite the original integral in terms of u. So note here that 1 over x does indeed appear. The rewrite is, instead of 1 plus natural log x, I replace that with a u and write that as u squared. Instead of the 1 over x dx, I replace all that with a du. There's no single part of this original problem that isn't represented either with the u or the du. So now I've got to integrate this simple scenario, add 1 to the exponent, divide by the new exponent. I get u cubed over 3 plus c. Now the back sub, you could be working in front of me. And I get 1 plus natural log x all cubed divided by 3 plus that constant c. So that's how that clock ticks. One more example, and again, this is the toughest of the 3, although I think you'll be in great shape. Take a look. This problem is integrate x cubed minus 1 all raised to the 4th times x squared dx. Set u equal to an inside function whose derivative appears. Well, I see the inside function. It's x cubed minus 1. My problem is, in my mind's eye, I'm taking the derivative of that expression and getting 3x squared. My problem is, I see the x squared, but I don't see the 3. So du does indeed equal 3x squared dx. And my predicament is, yep, I see the x squared. That part of the derivative appears. X squared appears. But what about that 3? So the technique here, whenever the derivative does appear, but you're just off by a constant that you need to do what we term as offset that constant. So the note is that you must offset that 3. In other words, there's an understood 1 here in front of the x squared. Well, what's the multiplier I need to utilize? What do you multiply 3 by in order to kick out a 1? That answer is 1/3. So the way you use this offset is you start the integral with that offset of 1/3 and then write down the remaining integral in terms of u. 1/3 times the integral of u to the 4th du. Integrate. Add 1 to the exponent, divide by the new exponent. Get 1/3 times quantity u to the 5th over 5 plus c. Now I'm going to back sub. I'm also going to take those two constants, 3 and 5, and write that as 1/15. The back sub in 4u, I put in x cubed minus 1. Now all raised to the 5th power plus c. Hopefully you can recognize here, and some of you that are strong with derivatives can actually see this with your mind's eye. But if you take that final answer inside that aqua rectangle, and you take its derivative now. If you take that derivative, you should get the original integrand in the original problem. If you take the derivative of the expression in that aqua rectangle, that's going to require the chain rule. So you take the derivative of the inside function, which you see is 3x squared, and when you do the multiplication, the exponent times the constant in front, you'll get 5/15 or 1/3. And then the other times 3 comes from the derivative of the inside function. That's what's going to eliminate constants altogether. That's why you don't see any constants in the original integrand. So when you are through, you get 1/15 x cubed minus 1 all raised to the 5th plus c. That's u sub. Again, the nuts and bolts of a u sub problem. You got to set u equal to an inside function whose derivative appears. Don't force the issue. And the other warning is you can only be off by a constant. You can only offset a constant. No variables allowed in your offset. If you find that you're offsetting something by 3 over x or something like that, the fact that you have that variable in your offset means you got to use a different technique other than u sub. You got to turn the page and rely on something else. So offsets are only allowed with constants. So make sure you remember that as you go through these problems. Get some practice. Indefinite integrals with u sub. Good luck. Over and out.